everyone, my name is Fares Abawi. Today I want to talk about gaze-aware dialogue systems, and more specifically about how integrating visual attention into voice agents can improve turn-taking and reference resolution. My broader argument is that gaze is missing a modality on the web, and that it deserves serious consideration in future web standards. Most voice agents today rely almost entirely on acoustic signals. They wait for speech, react to it, and then respond. This approach works reasonably well until a user says something like, this one or that button. At that point, the agent has no way of knowing what the user is referring to because it cannot see where the user is looking. In human conversation, however, we do more than just listen. We also watch. Gaze often reveals intent before someone starts speaking. It shows us what they are referring to, and it helps coordinate turn-taking. Voice agents today are missing this entire channel. So the question I want to ask is whether we can bring gaze to the web and what it would take to standardize it. There are three tasks where gaze integration is especially useful. To begin with, considering turn-taking coordination. Gaze shifts often precede speech by several hundred milliseconds. If an agent can detect these shifts, it can begin preparing a response early instead of waiting until the user finishes speaking. A second task is barge-in detection. When a user fixates on an interface element while the agent is speaking, that fixation often signals an intention to interrupt. If the agent can recognize this signal, it can yield the floor naturally rather than talking over the user. A third task is reference resolution. When a user says open that while looking at a specific button, gaze can be mapped to the document object model, or DOM for short. This allows the agent to resolve the reference immediately without asking follow-up questions. This slide shows the overall pipeline I'm proposing. We begin with three input streams. The first is gaze, which would come from proposed gaze tracking API. The second is voice, which is captured through existing media capture APIs. The third is user interface structure, which comes from the DOM and the accessibility tree. These inputs then pass through a normalization stage. During this stage, gaze is processed entirely on the user's device and no raw audio is retained. After normalization, all inputs are aligned on a shared timeline. This step is especially important because gaze typically leads speech. Once everything is temporally aligned, the system performs multimodal fusion. A shared encoder combines gaze, speech, and user interface context into a single representation. Finally, task-specific components produce structured events. These include grounding events that link speech to the DOM elements, turn-taking events that predict conversational floor state, and barge-in events that signal interruption intent. These events are then used to drive agent behavior, such as highlighting elements or yielding the floor. I would now like to describe each stage in a bit more details. There's the acquisition stage, which relies on web APIs. A permission-gated gaze tracking API provides gaze signals. Media capture supplies audio input. The DOM provides element roles and bounding boxes. And then next comes the normalization. At this point, all inputs are converted into a unified schema, and privacy is enforced by keeping gaze processing on device. Temporal alignment follows. Because gaze can lead speech by up to 500 milliseconds, the system uses a sliding context window that captures this anticipatory information. After alignment, fusion takes place. Cross-attention is applied across all three modalities, and a policy layer ensures that user consent and confidence thresholds are respected. The final stage consists of task-specific heads. One head resolves deictic references, another predicts conversational turn-taking, a third detects barge-in events, and each of these heads produces structured outputs that downstream agents can consume directly. There are several architectural options for multimodal fusion, and standardization could help clarify these choices. One option is early fusion. In this approach, embeddings from all modalities are concatenated at the input level. This keeps latency low, but it can obscure modality-specific patterns. Another option is late integration. Here, each modality is processed independently and combined only at the decision stage. This improves flexibility, but it also increases latency. A third option is cross-modal attention. With this approach, gaze representations attend to speech and user interface elements. This has proven especially effective for resolving deictic references. A fourth option involves gated multimodal units. These units dynamically control how each modality contributes to the final representation, and it's particularly useful for robustness because the system continues to function smoothly when gaze data is noisy or even unavailable. So this table summarizes the trade-offs among these approaches. Early fusion provides low latency, but it offers limited robustness. Late integration improves robustness, but it does so at the cost of speed. Attention methods or attention-based methods achieve high accuracy, particularly for reference resolution, but they require more computation. Gated units, on the other hand, tend to balance latency, robustness, and accuracy. In practice, hybrid approaches appear the most promising as they combine the best of all of these elements. By combining gated units with cross-modal attention, systems can achieve strong performance while still degrading gracefully when a modality is missing. The best choice really depends on the practical constraints. So real-time interactions favor early or gated fusion, scenarios with missing modalities favor gated or late integration, tasks that rely heavily on reference resolution benefit the most from attention mechanisms. There are several challenges that arise in real-world deployments. From a technical perspective, webcam-based gaze tracking has an error of roughly 4 degrees. This level of accuracy works well for large interface elements, but is not sufficient for precise text selection. Latency is another problem. For turn taking to feel natural, the end-to-end delay must remain below approximately 100 milliseconds. Robustness is also yet another challenge. So the lighting conditions change, head poses vary, and users may look away from the screen. So from a visual perspective, this could also cause a barrier that may be difficult to overcome when it comes to capturing the gaze of the user. From a deployment standpoint, systems must ensure explicit user consent. So we need transparent policies and strict guarantees that the gaze processing occurs on device. Finally, accessibility is critical consideration as well. For some users with motor impairments, gaze may serve as a primary input modality rather than a secondary enhancement. At the same time, reliable fallbacks are essential when gaze input is unavailable. Given these challenges, what should the World Wide Web Consortium consider standardizing? One important step would be gaze tracking API. Such an API could build on existing libraries like WebGazer.js, define calibration protocols, and specify privacy-preserving data formats. Like camera access today, it should be permission-gated and fully controlled by the user. A second step would be a voice agent multimodal extension. This would define how gaze integration with voice frameworks and how reference resolution should behave across different implementations. A third step involves accessibility guidelines. These guidelines should explicitly recognize gaze as an assistive technology and require meaningful feedbacks. So in case gaze is not available, it should still function as usual. I would like to close with a few open questions. One is, what level of accuracy is acceptable for practical deployments in terms of the accuracy of the gaze precision and in terms of the alignment? The second is, how should calibration work when the user expects the system to function immediately? So what would be considered excessive and what would be considered necessary for the system to function? Finally, I would also consider how we should balance privacy and utility in a way that earns the user trust. I don't have a definitive answer to these questions yet. However, I hope we can help frame future discussions research. Thank you for listening. My email address is on the screen and the slides are available on my website. I look forward to this discussion and to hearing your perspectives on how gaze-aware voice agents might move towards standardization.